lectures on simple harmonic motion, and first we're going to just kind of review what we know so far. Okay, we've talked about the restoring force, Fs, that's the force of the spring that acts against the mass, and the spring constant or force constant, K, which is measured in Newton meters, frequency, which is measured in hertz, period, which is measured in seconds, and angular frequency, which is measured in radians per second. In the formulas that we learned that the restoring force, Fs, is equal to negative Kx, where generally we're putting a mass on there, and we're just going to use that weight as the restoring force. And then the period, which is the time for one complete oscillation, is 1 over F, and vice versa. So if it makes 10 oscillations in 10 seconds, then the frequency would be 10 divided by 10, and then the period would be 1/2 of that, the inverse of that. And omega is 2 pi f, or 2 pi over period, because it's inversely related to that. And then we also had this generic formula for the position function here. All right, so let's just warm up and do an example. I give you this formula, 2 centimeters, cosine of 2 pi t, and we're going to find the period, the frequency, the angular frequency, and the amplitude. Well, first of all, the amplitude is easy. It's 2 centimeters, or 0.02 meters. The angular frequency is 2 pi radians per second. The frequency is going to be related to that. Or 1 hertz, and the period is 1 over F, which is 1 over 1, or 1 second. Now, to be fair, if you were doing this as a problem on a work set, would want this to 3 sig digs, 0.0200 meters. You can leave 2 pi radians as is. This would be 1.00 hertz, and this would be 1.00 seconds. All right, you should also be able to, if I give you information, find A and omega and write the generic position function. Stretch 5 centimeters, so A is 5 centimeters. Cosine of omega. So omega is 2 pi times the frequency. So let's find the frequency. The frequency is going to be the number of oscillations per second. Well, there's 10 oscillations in 5 seconds, so the frequency is 2 hertz. Omega is 2 times 2 hertz, or 4 pi radians per second. So our generic thing would be 4 pi radians per second times time. Okay. All right, so and we've already talked about angular frequency and mass. That angular frequency squared is equal to K all over M. All right, now let's talk about what the velocity function would look like and what the acceleration function would look like. So remember that on an xt graph, slope is velocity. So if I take the slope at time equals 0, it's 0. And the maximum negative slope occurs here. So velocity would plot here. The slope here is 0. Slope here is maximum positive. Notice that this cosine graph, the velocity looks like a sine graph, but it's an upside down sine graph. So this would be sine negative AW sine of omega t. And that the slope of a velocity graph is acceleration. So if I take the slope here, it's going to be a positive negative number. If I take the slope here, it's going to be 0. Take the slope here, it's a positive maximum number. The slope is 0 here. So I get a cosine graph again, but it's upside down. So the generic formula for the acceleration will be negative a w squared cosine of w, or omega t. So let's just do an example. If this is 2 meters, cosine of pi t, then this is going to be negative 2 meters times pi, so negative 2 pi meters per second, because it's velocity, times sine of pi t, because that's what omega is. And this one is going to be this number times pi again, or negative 2 pi squared meters per second squared times cosine of pi t.